Hello, this is Ana Doblas. Today's video is the second video for polarization optics for the course ECE 513 Intro to Optics and Photonics. In today's video, we're gonna define birefringent materials. We're gonna describe how optical retarders can change the polarization state of light. In particular, we're going to talk about how to predict the polarization state after polarized light transfer passes through full wave, half wave, and quarter wave plates. We're going to introduce the Stokes parameters and interpret them in terms of how we can measure it. And then we're going to assume like we have an incoherent superposition of two polarized beams. And we're going to talk about the resultant Stokes parameter. So birefringent crystals like quartz or calcite are materials that they're going to have different refractive index. Most of them have two unique refractive index. So we're going to introduce like the extraordinary and the ordinary refractive index that's gonna make one is gonna be different to the other. So we create like the birefringence, which is the difference between the refractive indices. And the reason behind is that light traveling along the glass is gonna have two distinctive waves within them, and the velocity of the light is gonna change based on the polarization axis and the polarization state. So some examples of birefringent optical elements are the nickel, Glan-Thompson, and the Glan-Foucault prisms. As you can see here, like you're gonna have unpolarized light or light with two orthogonal polarization state, which the orthogonal is across the perpendicular and parallel axis of the glass of the prism. And then when it goes within one of the three prisms, you're gonna decouple it, you're gonna detangle, and you're gonna have like the extraordinary and ordinary rays that they're gonna have orthogonal polarization state between them, leave the prism at different sides of the prism so they don't overlap. In contrast to that one, we have the Wollaston prism, where still at the exit of the prism, we have two orthogonal polarization states, but the two beams leave the same side of the prism. And because they are two orthogonal, they don't gonna create coherent interposition or interference with them. Another example is polarized beam splitters. Sometimes that's another close to the nickel prism where the orthogonal leave different polarization state, and that's really useful sometimes to build optical systems. So what is a retarder? Retarders, or also found on the literature as wave plates, are optical elements that they change the polarization state of the light. So it's like a linear polarizer, because on the linear polarizer we change, but we also reduce the amount of light. The retarders are meant only to change it's meant to delay one of the components versus the another without changing the amount of light. The amount of phase delay that one of the components of the electric field suffer is gonna depend on the thickness and also the wavelength. So those elements are mostly wavelength dependent. Every time that we are defining a retarder or a wave plane, we're gonna define two axes. We're gonna talk about the fast axis. That is the one that is gonna introduce the delay. And then we're gonna do the slow axis. So we're gonna use retarders as we were saying to change the polarization state, but it's really useful to move from linear polarization to circular polarization. So as here in this plot we are showing, let's say that you have, for example, linear polarized light at 45 degrees. So if you introduce a delay of half pi, then you can go to your right hand or your left hand linear circular polarization. If you have a delay of pi, then you can change from your positive 45 degrees, you're gonna have your negative 45 degrees, right? So it's gonna help us to move, but mostly we're gonna use, say, for moving to linear to circular polarization light. We were saying that the amount of phase retardance introduced between the two components of the electric field is wavelength dependent, and it's also gonna change on the thickness of the retarder. So definitely the birefringence, it's material given. That's gonna be defined by the material, but the thickness and the wavelength is something that one can specify when they are building or they are manufacturing the retarder or the wave plate. So we have three types of wave plates. The first type is the full wave plate. So that introduces a phase of 2 pi. So that means that we just make a whole cycle. So if we our polarization state remains invariant. It looks like we are not doing anything at all. The half plate is where our phase delay is gonna be pi. So what is gonna happen is that if we have linear circular line at 45 degrees, we're gonna shift it to minus 45 degrees, but still linear polarization. Or if we have left hand circular polarization, we're gonna shift it to right hand circular polarization. So it's always gonna be rotation of pi. The third type is quarter wave plane. So quarter wave plane have a phase delay of pi and a half. So what we are doing is moving within our quadrants, and that's the one that if we have linear polarization, we can go through circular polarization, or backwards. If we have circular polarization, we can go to plus or minus 45 linear polarization state. So the Stokes parameters and the Poincare are two kind of similar ways to understand the polarization state. So the Stokes parameter give us some quantification about what is gonna be the polarization of the technique. And as you see here, they give us the relationship with the Stokes parameter. So just as you know, just want to give insight here, these are kind of normalized Stokes parameters. So that means that S1 is over S sub 0, the total amount of intensity. So every time that you have a particular polarization state, you can define its corresponding Stokes parameter. And the Stokes parameter are uniquely defined for every polarization state. So here we provide a couple of examples about what is going to be the Stokes parameter with horizontal or vertical linear polarized, or linear polarization of plus or negative 45 degrees, or circular polarization. How are we going to measure the Stokes parameter? So the basic or the most traditional method requires a linear polarizer, a quarter wave plate, and a photodetector. So the first one is you have your light source, and then with the photodetector you measure the total intensity without the polarizer or the retarder. Then you place the polarizer and you rotate it, so you have horizontally linear polarized light, and then you rotate it 90 degrees, and then you have vertically linear polarization light. And that's how you get your S1 Stokes parameter. For getting your third Stokes parameter, what we need to do is you need to rotate the linear polarizer, but to the plus and negative 45 degrees. And then you do the subtraction of those intensities. And finally, after the linear polarizer, you introduce the quarter wave plane to change the linear polarization state to circular polarization. and then you rotate it to have right hand circular polarization and left hand, and measure the intensity and do the subtraction to estimate S3. Obviously, there is already a polarimeter that gives you automatically the Stokes parameter, and there are methods to do it, but that's how basically you're gonna do it. When you define your Stokes parameter, there are 4 different values, right? So you can talk about the degree of polarization, which is gonna be the square root of S1 squared plus S2 squared plus S3 squared divided A sub 0. And remember, S sub 0 is the total intensity of your light source. So the degree of polarization needs to change from 0 to 1. Meaning 0 that it's for unpolarized light, so natural light, and 1 when you have a clear polarization state, so linear or circular polarization state, and any elliptical state is within the middle. So something that is super useful when you have a Stokes parameter is because you can do incoherent superposition of them. So let's assume that you have 2 beams of light that they are incoherent, and each of them you have characterized the polarization state based on the Stokes parameter. So you can define the resultant Stokes parameter of the light by superposing the individual Stokes parameters. So it's gonna be 1 plus 1 minus 1 plus 0, 0 plus 0, and 0 plus minus 1, right? So the resultant Stokes parameter is going to be 2 minus 1, 0 minus 1. And now this is going to be it's going to represent the polarization state of your resultant. And now you know, like, your degree of polarization of the resultant is going to be S1 squared plus 0 squared, 2 squared plus minus 1 squared divided 2. And so, so that's gonna be a square root of 2 over 2, so 1 over square root of 2, that's gonna be the degree of polarization. And remember, the degree of polarization needs to be always between 0 and 1. I hope that this video helped you to understand more how is the working principle of the retarders and the Stokes parameters. Thank you. These are additional resources for you to watch if you want to know or clarify some concept of this video.